This is slide number 37 and I am your presenter Asloob Mudassar. Diffraction by a planar screen. You see that in the picture we have shown a screen which is opaque extending to the infinity, and between the two opaque apertures there is a clear aperture or small opening labeled as S1, and the opaque aperture has been labeled as S2 on both sides of the clear aperture. The aperture is incident with a normally incident unit amplitude plane wave. The arrows shows the direction of a propagation of the plane waves, and you know that there is a point of observation P0 at which we want to calculate the field. That is the field which is incident from the left side on the aperture. We want to calculate the contribution of that field at the point P0. And there is another surface, hypothetical surface S3, which has a radius capital R, and the curvature is centered at the point P0. This omega is actually the solid angle that the surface S3 is projecting at the point P0. Now consider another point P1 which is lying on the clear aperture S1. So P1 is any point on the aperture S1. The radius, the position vector of this point P1 with respect to P0 is R01, and n hat is a unit vector at the point P1 to the surface S1, and this is normal to the surface S1. So we have to calculate the field at point P0. We shall take into account the contribution due to the surface S. We shall take into account the contribution of the surface S2 at point P0, and similarly we shall take into account the contribution of the surface S3. And the field that is incident on the aperture will be regarded as capital U as the field incident on that one. So let's read something more about this picture. Consider an opaque planar screen which is infinite in extent and has a small clear rectangular opening. So actually in two-dimensional space this is a rectangular opening, but you know that in one-dimensional picture we cannot show the rectangular opening. So this is actually a gap between the two opaque regions. So actually in principle this is a rectangular aperture. When plane waves pass through such an aperture, a diffraction will occur at the edges of the transparent part of the aperture, and a diffracted field will contribute in the space to the right of the diffracting aperture, that is at point P0. We want to assume the diffracted field, say at point P0, located on the right side of the diffracting aperture using integral theorem of Helmholtz and Kirchhoff. So we are going to calculate the field at point P0 due to the Helmholtz and Kirchhoff theorem. We have integral theorem of Helmholtz and Kirchhoff, which we have already derived. Now the optical disturbance incident on the aperture is labeled with a capital U. To construct the Green's function, it is assumed that a point source is located at the observation point P0, which generates spherical waves all around. So you see that here in this picture we are assuming that a hypothetical Green's function is located at point P0, which is generating spherical wave all around. And that is why you can see that the surface S3 is the surface at which the contributions of the Green's function will reach. The contribution of the Green's function will also reach all around, that is on the surface S1, on the surface S2, and on the surface S3. And it is a spherically diverging source located at the point P0. The value of the Green's function due to the point source at P0 on the hypothetical spherical surface ST centered about the point P0 is given by. So this is the contribution of the Green's function that you can see at the point P0. So G of R is equal to e to the power iota k r over R, because G is a point source located at the point of observation P0. So this makes equation 25. Two extra surfaces S1 and S2 are drawn just after the aperture, so that S1, S2 and S3 form a closed surface. P1 is any point on the clear aperture at a distance R01 from P0. the field at P naught using equation 23 is given by. So we are using equation 23 to calculate the field at point P naught. So field at P naught, that is u of P naught, is equal to 1 over 4 pi double integral over each of the surfaces, over each of the three surfaces, that is on surface S1, surface S2 and surface S3, and the integrand is g curly u over curly n minus u into curly g over curly n, and the integral element ds. So you see that this is the integral that we have to solve for each of these surfaces. This integral needs to be solved for the three surfaces S1, S2 and S3. For the surface S3, the Green's function, that is equation 25, is known. So this is known, you know that equation 25 is known at the surface S3. For the surface S3, the Green's function equation 25 is known and the integral is given by. So let's attempt to solve the integral over the surface S3. We have u of P naught is equal to 1 over 4 pi, and both integrals are on the surface S3 because we want to solve first for the surface S3, and the integrand is the same. Now we have converted this surface integral into the solid angle geometry, and the single integral is over the solid angle omega, and we have the same integral, and we have the sphere element as 4 pi r square omega, and 4 pi will be cancelled out with the 4 pi outside the integral. So we have this integral as given in equation number 27. So we have to solve this integral. On the surface S3, we are going to calculate, you know that we have to calculate the parameters shown in equation 20 number 7. We have to calculate these parameters, that we have to calculate partial derivative of u with respect to n, the partial derivative of j with respect to n, etc. So let's calculate partial curly r over curly n, and you know that from the geometry it is clear that r and capital R and n both are making an angle 0 with each other. So cos of n hat comma r is equal to 0 and the cos of 0 is equal to 1. And now we are going to calculate the partial derivative of curly g with partial derivative of g, that is curly g over curly n. And we are using g as we have stated in equation number 25. We are substituting the value of g over here, and then you know that we have computed this first part on the right hand side, and then we have introduced capital G back where possible. So we have second last term is capital G, within the parenthesis we have iota k minus 1 over r. And if we substitute that r is very large, that is the surface S3 is very large, then you know that the contribution of 1 over r will be equal to 0, and we are left with the partial derivative of g with respect to n is approximately equal to iota k into capital G, under the assumption that the surface S3 has a very large radius. Now using equation 28, equation 27 now takes the form. So look at this integral again. So we are solving this integral. You know that the integral over the surface S3, we have solved we have written it in the form of the solid angle integral, and we are now substituting the value for partial derivative of g with respect to n. So this is what we have substituted the value. Now we have arranged the terms, that is we have arranged r square. So these are 2r into r. One r we have used with capital G, the other r is what we have used with these parentheses. So because we are going to use some trick over here, some condition. So this is the Sommerfeld condition that we are going to use. This is the Sommerfeld condition, and it is a part of the integrand in equation 29. So look at this r, and within the parenthesis we have a partial derivative of u with respect to n minus iota ku, and r goes to infinity implies that this whole value will be equal to 0. This is the Sommerfeld radiation condition in order to solve this integral, and you know that under this condition the integral in equation 29 will be equal to 0. So the integral over the surface S3 will be equal to 0. But you know that we have to do some justification, we have to provide some justification for using the Sommerfeld radiation condition, that is equation 30. So let's find out the justification. So justification of Sommerfeld radiation condition. It will be justified only provided we assume that capital U behaves as a diverging spherical wave, that is capital U is equal to e to the power iota k r over r. So this field is incident from the left hand side on the aperture as a spherically diverging wave. So you know that here in the picture we have shown that plane wave is incident on this one. Now we are assuming, to justify the Rayleigh-Sommerfeld condition, we are assuming that a spherically diverging wave is a incident on this surface, on this aperture, rather than the plane waves. So under that condition we have to satisfy the Rayleigh-Sommerfeld radiation condition. So we have written the contribution of capital U on the aperture, which is equal to e to the power iota k r over r. It means that the diverging source U, capital U, is located at a distance r from the aperture. Now what we are going to do is that we are substituting the value of U over there, and we are going to calculate the partial derivative of U, which is here the value of U is e to the power iota k r over r, and we are taking the partial derivative of this quantity with respect to n. And the other term is minus iota ku, and on the left hand side we have the limit r goes to infinity. So after calculating its partial derivative, we are substituting back in terms of capital U. So we have in the parenthesis iota ku minus U over minus capital U over r minus iota ku. So you know that iota ku, there are two terms iota ku, one with the positive sign, the other with negative sign. They will cancel out with each other, and we are left with minus limit r goes to infinity capital R multiplied by U over r. So you see that we have to use these limits, and when we want to calculate the contribution of capital U at the surface R, at the surface S3, then we have to use the radius R, we have to replace the small radius R with the capital R, and the limit is again r goes to infinity. So these two r will cancel out with each other. We are talking about in the second row of equation 31, and we are left with the minus limit r goes to infinity applying to capital U, and again the value of the U is e to the power iota k r over r. So if you put the value for r goes to infinity, the denominator, the r in the denominator will dominate, and we will ultimately get 0. So this is in the equation we have in the equation 31 we have provided the justification of using the Sommerfeld radiation condition. And we have assumed that U is not a plane wave, but is actually a diverging, is a spherically diverging wavefront incident on the aperture. Now S3 is a hemispherical cap, and when the hemispherical cap expands with the radius approaching infinity, the contribution of the optical disturbance U on S3 approaches 0, as clear from equation 31. The contribution of the optical disturbance on S3 at the point of observation P0 is thus 0, and the integral in equation 26 reduces to. So you know that we have proved that the contribution due to the surface S3 is 0. So we are left with only two surfaces from which we have to calculate the contribution at the point of observation P0. So over U of P0 is equal to 1 over 5 with the two surface integral, one on S1, the other is on S2, and the argument you know that is the same as we have in one of the previous equations. So now we have to solve equation 32, that is we have to calculate the contribution due to surface S1 and S2. Now here Kirchhoff has made some assumptions. So let's say what Kirchhoff assumed. Capital U and its partial derivative with respect to n are both 0 in the opaque region S2 of the planar aperture. So you see that U and its partial derivative both are 0 in the opaque region. That is, after the opaque region both are 0. So this is the one condition, that the assumption that the Kirchhoff assumed. And what is the second condition? U and its partial derivative in the open region S1 of the planar aperture, that is in the clear region of the aperture, are the same as they were in the absence of the aperture. So if whether the aperture is there or not there, then after the clear aperture U and its partial derivative are the same as if the aperture is not present. So two assumptions. One is after the opaque region that is u and its partial derivatives both are 0, and after the clear aperture u and its partial derivative are the same as if the partial derivative is not present. So you see that under these conditions, if both u and its partial derivatives are 0 with respect to the surface S3, then you know that you put u is equal to 0 and partial derivative of u is equal to 0 in equation 32. Then of course the integral over the surface S2 will vanish out. So under these conditions that the Kirchhoff assumed, we have double integral over the surface S2 is equal to 0. So it means that under the Kirchhoff's conditions, after using these conditions, we are left with only one surface, that is the surface S1, at which we have to calculate the contribution due to the surface S1 on the point of observation P0. So as established, the contribution at P0 due to the optical field at S2 and S3 are 0, and we are now left with u of P0 to be calculated from the integral is equal to 1 over 4 pi. The surface integral is only on the surface S1 now. It is the same integral, that is g into the partial derivative of u with respect to n minus u into the partial derivative of g with respect to n, and the whole bracket is multiplied with the surface element ds. So this makes equation 33. So this states that the contribution at the point P0 is only due to the surface S1, and which is of course incorrect, because the physical conditions are different from that one. Because in the physical conditions you can also notice that there is a field, that you can also detect a field behind the opaque aperture, that's the opaque region of the aperture, where we have assumed that the partial derivative of u and u itself both are 0. But you know that since we have observed the field behind the opaque aperture, it means that u and partial derivative of u cannot be 0. So we cannot set the surface integral over the surface S2 equal to 0. So you know that the contribution at the P0 will be only due to the surface S1 as given in equation 33 is obviously incorrect. Now Kirchhoff boundary conditions are incorrect. So let's see how. In the geometrical shadow of the aperture S2, the field diffracted from the aperture is observable. So you know that this is the very important point, that after the opaque aperture you can observe the field. Due to diffraction, the field may extend several wavelengths both in the region against the open aperture and in the region against the opaque aperture. So u and its partial derivative just after the open aperture would be different from their values just before the aperture. So 2 points we got from this statement, that u and its partial derivatives, that is u and curly u over curly n, both cannot be 0 behind the opaque aperture. The second point we have got is that u and its partial derivative both cannot be the same behind the clear aperture. So both cannot be 0 behind the opaque aperture and both cannot be the same behind the clear aperture. So justification of equation 33. What is the justification provided by for the equation 33? You know that when these conditions are not correct, then you see that there must be some justification to make it to appear approximately correct. So this is the justification for equation 33. The integral in equation 33 will only be approximately correct if the size of the open or the clear aperture is much larger compared with the wavelength of light, in which case the amount of diffracted signal will be relatively smaller in comparison with the undifracted beam. So you see that over clear aperture is larger in size in comparison with the wavelength of light, larger, such that the amount of diffraction is very small in comparison with the undifracted beam, and so we can neglect the contribution of the diffracted field. Simplification of equation 3 will be made by the Fresnel and Kirchhoff. They assumed that the source point and the observation point are many optical wavelengths away from the diffracting aperture. So you see that in the next slide we shall be discussing more detail from the Fresnel and Kirchhoff, that the simplifications they provided in connection with the equation 33 with the assumptions that the source point and the observation points are many optical waves away from the diffracting aperture. So this ends the slide number 37.